Hello friends, today we'll discuss one more result, that is stable subspace theorem. In the previous lecture, we have seen how to obtain generalized eigenspace. Generalized eigenspace. Okay. What about that? If your lambda is the eigenvalue, then it is a solution of a minus lambda I operating on a vector v equal to 0. Then this non-zero vector v is called eigenvector, and the set of all eigenvalues is called generalized eigenspace. Now we will go for stable subspace theorem. Stable subspace theorem. Suppose lambda 1 up to lambda n, not necessarily distinct, be the eigenvalues of matrix A, arranged so that lambda 1 up to lambda k are the eigenvalues with modulus less than 1. Let S be the k-dimensional space spanned by the generalized eigenvectors corresponding to these eigenvalues lambda 1 up to lambda k. Okay. S is what? S is what? S is the k-dimensional space spanned by the generalized eigenvectors, and the eigenvectors are corresponding to these eigenvalues having modulus less than 1. If U is the solution of then system of homogeneous equations with initial vector in S, then ut, which is the solution of this system, is also lies in S for t greater than or equal to 0, and limit as t tends to infinity, u of t should be equal to 0. Now, previously we have seen what about generalize the eigenvector. Okay, we have then the generalized eigenvectors of A corresponding to lambda are the non-trivial solution of A minus lambda I to the power m operating on V equal to 0. Why m is there? If lambda is the eigenvalue of A with multiplicity m, then the set of corresponding eigenvector is called generalized eigenvector, isn't it? Generalized eigenvector. And we have obtained generalized eigenspace in last lecture. So 3, 3, 2 are the eigenvalues corresponding to lambda 1 equal to 3. We obtain eigenvector V3 equal to 0. The basis of eigenvectors are this one, and these are the basis of eigenvectors 1, 0, 0, 0, 1, 0. This is the two-dimensional space. Similarly, with respect to lambda equal to 2, we obtained V2 equal to 0, V1 equal to 0. This is the basis of one-dimensional, isn't it? So now here we want to consider only those eigenvalues whose modulus is less than 1. Whose modulus is less than 1. Okay. Let U be the solution of U of t plus 1 equal to AUT with U of 0 in S. Since A takes every generalized eigenspace into itself, it also takes S into itself. Then U2 is in S for all t greater than or equal to 0. Choose delta so that maximum of modulus of lambda 1 up to lambda k, which is less than delta and which is less than 1. Thus there is a constant b greater than 0 such that mod of CIT less than or equal to b times delta t. This already we proved here. If lambda 1 up to lambda n are the eigenvalues whose modulus, maximum modulus is less than 1, then we have already proved this. Mod of CIT less than or equal to b times delta to the power t in one of the previous lecture for t greater than or equal to 0 and I lies between 1 to 3. So we also know that u of t is given by, which is the solution I from 0 to n minus 1 ci plus 1 of t mi into u of 0. By definition of mi and the fact that u of 0 is a linear combination of generalized eigenvectors corresponding to lambda 1 up to lambda k. U of 0 is what? Combination of generalized eigenvectors corresponding to lambda 1 up to lambda k, that is u of 0 is something eigenvectors is there v1, something c1 v1 plus c2 v2 plus up to plus ck Pk. This is your u of 0. Okay. Therefore, for I greater than or equal to k, mi u of 0 must be equal to 0. Mi u of 0 must be equal to 0, as u0 is only linear combination of this and remaining term will be 0. Therefore, mod of ut less than or equal to I from 0 to k minus 1, mod of ci plus 1 of t into mod of mi u of 0. For this, we have seen it is less than or equal to b into delta to the power t. We know that for any vector mod m into v less than or equal to some k times mod v, by using that, it's some constant times mod of u of 0, that is outside, isn't it? That is outside, and mod of u0 is outside. This is some ci, I from 0 to k minus 1, it is some d, and d into b, we have taken it as c into delta to the power t mod of u0. Now, as this delta is less than 1, so as t tends to infinity, delta to the power t must tends to 0 for t tends to infinity for some constant c, and therefore limit of ut as t tends to infinity equal to 0. So what we obtain there? The solution, the set of solutions corresponding to solution of this homogeneous system, u of t plus 1 equal to aut tends to 0 if your lambda 1 up to lambda k are the eigenvalues with mod of lambda less than 1, and so solution is stable in this case because each solution approaches to origin, and therefore we say that the system is stable, that is solution is also stable. Okay, the set S in above theorem is called stable subspace for ut plus 1 equal to aut. What is S here? S is the set of only those eigenvectors which are corresponding to such eigenvalues whose modulus is less than 1. Also note that every solution of system that goes to origin as t tends to infinity must have its initial point in S. Its u at 0 must be belongs to S. Right? Thus, S can be described as the union of all sequences ut from t equal to 0 to infinity, that is u of 0, u of 1, and so on, that solve the system and satisfy this equation. We can find the stable subspace for the system. U of t plus 1 equal to, suppose your matrix is A is equal to this one, 0.500, 1, 0.50, 0, 1, 2. We want to find stable subspace means what? We want to find the space of such eigenvectors corresponding to eigenvalues whose modulus less than 1. Now, first of all, we will find the eigenvalues of this matrix, and therefore its a characteristic equation is determinant of lambda I minus A equal to 0. So lambda I minus A means lambda minus A, lambda 0, 0, 0, lambda 0, 0, 0, lambda minus A. So lambda minus 0.5. No, so 0 minus 0, 0 minus 0. So it is 0 minus 1, that is minus 1, lambda minus 0.50, 0 minus 1, lambda minus 2. Its characteristic equation becomes lambda minus 0.5 into lambda minus 0.5 into lambda minus 2 minus 0. All other terms are 0, so we get this as the characteristic equation. Lambda minus 0.5 whole square into lambda minus 2 equal to 0. Okay, so we get three eigenvalues here. One, lambda 1 is 0.5, second is also lambda 2 is 0.5, and third is only lambda equal to 2. So lambda 1 equal to 0.5, lambda 2 equal to 0.5, lambda 3 equal to 2. In these two, from these three eigenvalues, we got two eigenvalues whose modulus is less than 1. Okay. Now, the stable subspace has a dimension 2, and which contains the solutions of a minus 0.5 I square operating on v equal to 0. So now, what is a minus 0. Because 0.5 is repeating twice, that it has multiplicity 2. Therefore, it should therefore we are finding the v vector v satisfying a minus 0.5 I square operating on v equal to 0. So this is a minus 0.5 I, right? And this is also a minus 0.5 I. So it's a multiplication is, if I take first row with all these three columns, as each element is 0, so we get 0, 0, 0. Second row, first column 0, second row, second column 0, second row, third column, it also equal to 0. Now we get third row, first column, third row, second column, third row, third column. For third row, first column, we get 1 into 1, 1. Third row, second column, 1.5 into 1. And third row, third column, 1.5 into 1.5. That is 2.25. 2.25 can be written as 3 by 2, and this is, we can write it as 1 3 by 2 9 by 4. 1 3 by 2 9 by 4. v1 v2 v3 0 0 0. So v1 plus 3 by 2 v2 plus 9 by 4 v3 equal to 0. So this is your 4 v1 plus 6 v2 plus 9 v3 equal to 0. What about this? This is a plane. This is a plane passing through 4 6 9. This is a plane passing through the point 4 6 9. So this is the plane passing through the point 4 6 9, and it is nothing but our stable subspace of that V. So with respect to this stable subspace, this one, with respect to this plane, your solution becomes what? Ut into lambda to the power t operating on V. So this is our V, and we multiplied this by lambda to the power t, where lambda is now here what? 0.5 to the power t. And we know that as t tends to infinity, this whole will be approaches to 0, that is stable subspace. And therefore, this is called stable subspace of given system. Thus, every solution that originates in this plane remains in the plane for all values of t and converges to origin as t tends to infinity. Now, this is not stable subspace, but this is a eigenvector. Now, we will find another eigenvector corresponding to eigenvalue 2. So it should satisfy a minus 2I operating on v equal to 0. So minus 1.5 0 0 1 minus 1.5 0 0 1 0 v1 v2 v3 equal to 0. Okay. So if I multiply this, what about this? This is a minus 2I. A is what? A is your this matrix. 0.5 minus 2. Therefore, we get minus 1.5. 0 minus 0 0 0 minus 0 0. 1 minus 0 1. 0.5 minus 2. Because 2I is there. 1.5 minus 1.5 0 0 1 2 minus 2, you will get 0 there. 0. So if I solve this, we get first row, first column, that is minus 3 by 2 v1 equal to 0. First row, second row, first column, v1 minus 3 by 2 v2 equal to 0. And third row, first column, v2 equal to 0. Now v2 equal to 0 as well as v1 equal to 0, we get this. So v3 is anything. V3 is anything now. So V3 is anything. So 0 0 1 is an eigenvector corresponding to eigenvalue lambda equal to 2. This is not stable subspace. There is a solution originating on the V3 axis. Now we don't know what about this one. If this is a solution there, Okay. So with respect to lambda equal to 2, so 0, 0, 1 is an eigenvector corresponding to lambda equal to 2. Thus, the solution originating on V3 axis is given by ut is equal to lambda to the power t into this sector. Now V3 is non-zero, and as t tends to infinity, this whole tends to infinity, not tends to 0. This remains on the V3 axis and approaches to infinity in the positive or negative direction, depending on whether V3 is positive or negative. Okay, that is the case there. Now, okay. Now we have some more examples how to find the stable subspace S for each of the following. U of t plus 1 equal to 0, 1, 2 by 3 minus 5 by 3 operating on ut. A is 0, 1, 2 by 3 minus 5 by 3. So the characteristic equation is this one. Lambda I minus A equal to 0, which implies lambda minus 1 minus 2 by 3 lambda plus 5 by 3 equal to 0. So lambda square plus 5 by 3 lambda, right? Minus minus plus and then minus 2 by 3 equal to 0. So 3 lambda square plus 5 lambda minus 2 equal to 0. So if we write this, 2 3s are 6, factor 6 in such a way that the subtraction is 5. So we get lambda plus 2 into 3 lambda minus 1 equal to 0. So lambda equal to minus 2 and lambda equal to 1 upon 3. Now, for this lambda, its modulus becomes 2, and for this lambda, its modulus becomes 1 by 3, strictly less than 1. Therefore, we can obtain the subspace. Which subspace? That subspace with respect to modulus less than 1. So we want to obtain the eigenvector corresponding to this only to find stable subspace. So the stable subspace has dimension 1 and consists of the solutions of A minus 1 by 3 I operating on EV equal to 0. This is A minus I. Why A minus I is there? A is 0, 0 minus I, lambda I, 0 minus lambda I. Lambda is what? Corresponding 1 by 3. So we get minus 1 by 3. 1 as it is, 2 by 3, and minus 5 by 3 minus 1 by 3 as it is, operating on V1, V2 equal to 0. If we solve it, we get minus 1 by 3 V1 plus V2 equal to 0 as the first equation, and 2 V1 minus 6 V2 equal to 0 as the second equation. If we solve these two, that is, first is V1 minus 3 V2 equal to 0 is the stable both should same v1 minus 3v2. That means what? Only we get this as a stable subspace. What is it? It is a plane of one dimension passing through 1 comma minus 3. Plane in one dimension passing through 1 comma minus 3. It is a stable subspace. And so for lambda equal to minus 2, the eigenvector is a plus 2i operating on v equal to 0. So again, if I solve this one, we get 1 minus 2 is the eigenvector, and its corresponding solution is minus 2 to the power t. We know that as t tends to infinity, it will be tends to minus infinity. And this solution becomes what? 1 by 3 to the power t into v1 minus 3v2. And this will be tends to 0 as t tends to infinity. So in this way, we can find stable subspace. Now we will go for stability of nonlinear system. Suppose that we can write such an equation so that the value of the unknown at largest value of the independent variable is isolated on one side of the equation. So nonlinear system means what? The equation which is nonlinear. Nonlinear means what? We must get the power of 2 other than 1. That is y square t plus 1, the terms containing of this type, or yt into yt plus 1. An equation terms containing of this type. This is called nonlinearity. Okay. So we have to go for stability of nonlinear system. To see the stability of nonlinear system, we have some definitions are there. A vector u in Rn is a fixed point of f if f of u equal to u. A vector u in Rn is said to be fixed point of f if f of u equal to u. It is very basic definition of fixed point. A point x belongs to R is said to be fixed point of f if f of x equal to x. That means domain, the image of state number should be itself. That is called fixed point. A vector v in Rn is periodic point of f if there is a positive integer k, so that fk at v equal to v. Now here f of v equal to v implies v is a fixed point of f. F of v equal to v says that v is a fixed point of v. But if I take fk of v equal to v, k times f, if I operate k times f on v, then v is called periodic point of f. No doubt, every fixed point is a periodic point with period 1. Every fixed point is a periodic with period 1. But every periodic point may not be a fixed point, because fk at v equal to v may not be implies f of v equal to v. So here, and k is called period of v. So here fk of v means what? You are operating k times f on v. Know that a fixed point of f represent constant solution of ut plus 1 equal to f of ut, because f of a fixed point of f represent a constant, because what is it? F of ut equal to ut we have taken. So ut plus 1 equal to ut. If ut is a fixed point of f, you can write f of ut equal to ut. That is ut plus 1 equal to ut, and its solution is 1 to the power t. 1 to the power t means 1, so 1 is the solution. That is solution is constant. Note that a fixed point of f represent a constant solution of ut plus 1 equal to f of ut, and periodic points yields a periodic solution. The periods k is not unique, since any integral multiple of k is also a period. But every periodic point has least positive period called as prime period. For example, if you have f2 of v equal to v, then this will use f4 of v is also equal to v, means f square and its a square of v is equal to v. Similarly, f square and its a cube of v equal to v. That is, f6 of v equal to v you will get, isn't it? It is like that. Therefore, now if 2 is the period, then 4 is also period, 6 is also period, and 8 is also period. So there are many periods. If k is period, then other than k also there are so many periods, but the least period is called the has the least positive period, which is called the prime period. There are some examples on this fixed point or periodic point. For example, f of u equal to 2u into 1 minus u. If we have this one, this has a fixed point u equal to 0 and u equal to 1 by 2. How to find fixed point of this f then? Let f of u equal to u. That is, f of u is this one. 2u into 1 minus u equal to u. That is 2u into 1 minus u equal to 0. That is 2u minus u. 2u minus 2u square minus u. So you will get u into 2 minus 2u minus 1. If I take u common from these two, we get u into 2 minus 2u minus 1 equal to 0. So u into 1 minus 2u. 1 minus 2u equal to 0. So either u equal to 0 or 2u equal to 1, that is u equal to 1 by 2. It implies, therefore, u equal to 0 and u equal to 1 by 2 are the fixed point. That means to obtain the fixed point, we have to consider f of u equal to u and solve it, find the value of u. That will be the fixed point of u1. Now here, we'll go for one more example. F of u1, u2 equal to u2, u2 by u1. Now, two dimension we have taken. Which domain u1, u2? u1 not equal to 0, u2 also not equal to 0. u2 also not equal to 0, u1 also not. Now, every vector in the domain of f is a periodic point with period 6. The only fixed point of f is 1, 1. Okay. 3 points have at least positive period 3, but no point have least period 2. We want to go for this one by one. Okay. Now, first of all, we will obtain the fixed point of f. Let f of u equal to u. So f of u is what? u2 upon u2 and u2 upon u1, which should be equal to u1, u2 for this. This implies u2 equal to u1 and u2 by u1 equal to u2 again. Right? u2 by u1 equal to u2. That is u1 equal to u2. If I put here u1 equal to u2, so then it is true. It is true. So u1 equal to u2 and u2 equal to u1, u2. So we are getting here u2 equal to u1 as well as u2 equal to u1 into u2. u2 equal to u1 as well as u2 equal to u1 into u2. Therefore, u2 should be 1 and u1 also should be 1. Then and then only these will be satisfied. See here. That means what? u2 equal to u1 or u1 equal to u2 and u1 also equal to, now so here u2 equal to u1, u2. u2 equal to u1, u2. So what this implies? u2 equal to u1, u2 means if u2 is not equal to 0, u1 equal to 1. Put u1 equal to 1 here, we get u2 also equal to 1. So u1 equal to 1, u2 equal to 1. So u equal to 1, 1 is a fixed point for f. That we obtain. Here, the only fixed point of f is 1, 1. That we are at. Okay. Now we want to see every vector in the domain of f is periodic with period 6. Every vector means what? f6 of u1, u2 is equal to u1, u2 will get. Now we'll go for that. Now f square of u1, u2 equal to f of u1, u2. Now for this f of u1, u2, we have u2 upon u1 and again f on this. Right? Now f of u2 by u1. Now your f of u1, u2 is what? u2 means second component and u2 by u1. Right? Division of these two. Now what is f of u2 and u2 by u1? So second component here u2 by u1 and division of these two u2 by u1 upon u2. u2 by u1 upon u2 means u2 by u1, u2, which is equal to u2 by u1. Now the u2 cancels with u2 and we get 1 by u1. Now f of u1, u2 is u2 by u1, 1 by u1. These two are not same. So it is not equal. That is 2 is not period now. Now we will find f3. f3 of u1, u2. That is operate f on this. That is f of u2 by u1, 1 upon u. We know that the second component will be here, and this upon this 1 by u1 upon u2 by u1, 1 by u1 upon u2 by u1 means 1 by u1 into u1 by u2, so we get 1 upon u2. So again, f cube of u1 u2 is not equal to u1 u2. So this has u1 u2 is no periodic of period 3. Now f4 of u1 u2 means apply again f on this, again second component here, and this upon this 1 by u2 upon 1 by u1, that is u1 by u2 will get here. Again it is not same. f5 of u1 u2, again apply f on this component second, u1 by u2 is here, and u1 by u2 upon 1 by u2, that is we get only u1 here. Again apply f on this, that becomes f6 of u1 u2. If I apply f on u1 by u2 upon u1, second component becomes here, and this upon this u1 upon u1 by u2, that is u1 into u2 by u1 means we get u2. Now that means f6 of u1 u2 gives us u1 u2. Therefore u1 u2 is a periodic point of f with period 6. So u1 u2 means any vector. So every vector is a periodic vector of f with prime period 6. Okay, thus every vector in a domain of f is a periodic with period 6 that we obtain. Now f3 of u1 u2 is equal to u1 u2 implies, if I take f3 means if I take it is a period with period 3, then what will obtain? f3 of u1 u2, because f3 of u1 u2 is what? 1 by u1 1 by u2, yes, equal to u1 u2, that is 1 by u1 equal to u, and 1 by u2 equal to u2. So u1 square equal to 1, u2 square is also equal to 1. So u1 equal to plus or minus 1, u2 equal to plus or minus 1. So you will get 3 pairs there, minus 1 1, minus 1 minus 1, 1 minus 1 are the 3 points with least period 3 are the 3 points. If we take that one, you will get u1 and u2. So these are the 3 points with least period 3. That is which? Minus 1 1. So f cube of minus 1 1 becomes this one. F cube of minus 1 becomes same, and f cube of 1 minus 1 becomes same. So there are the 3 points. So 1 1 is the periodic point with at least period 1, because f of 1 1 is 1. That is a fixed point. Now if I take f square of u1 u2 equal to u1 u2, then u1 square u2 and u1 u2 is equal to 1. This is possible only if u1 1 u2 1, which is a fixed point, not periodic, with at least period 2. Now what we have proved here? Are all these conditions satisfied? See here, every vector in domain of f is a periodic point with period 6, that we proved. The only fixed point of f is 1 1. There is no other fixed point. 3 points have at least positive period 3, but no points have at least period 2. At least period 2, there is no point, because there is only 1 point with at least period 1. Okay, that's why we have taken f cube of v is equal to v, then you will get these 3 points. So these are the 3 points with at least period 3. And if we take f square of v equal to v, then we get this one. This is only possible if 1 1 is there, and that already we have counted. It is a fixed point. Okay. This is the third also example. F of u1 u2 equal to u2 minus u1, isn't it? This function rotates every vector 90 degrees clockwise. 0 0 is the only fixed point, and every other point is periodic with at least period 4. Here u1 u2 equal to cos theta sin theta. U1 f of u1 u2, let u1 u2 equal to what? Cos theta sin theta. What is f of u1 u2? F of u1 u2 becomes u1 u2. This implies, but f of u1 u2 is given by u2 minus u1. So u2 equal to u1 minus u1 equal to u2. u1 equal to u2, u1 equal to minus u2. Therefore u1 is 0 as well as u2 is 0. So 0 is the only fixed point of here. Only fixed point. Because for this case, u1 u2 same, and u1 their negative also same. There is only 1 point, u1 0, u2 0. Now f square of u1 u2, if I find it, then you will get minus u1 minus u2. F cube of u1 u2, that is apply f on this again, you get minus u2 u1. F fourth u1 u2 equal to u1 u2. Therefore, u1 u2 is a periodic with period 4. Thus every other point is periodic with at least period 4. Okay. There are so other examples are there to find fix the points for the following functions. F of u equal to 4u into 1 minus u. Let this is equal to u, find the value of u. So u equal to 0, u equal to 3 by 4 are the fixed points. Then for this also, f of u equal to 4 plus sin 8u. So let this is equal to u, sin 8u equal to 0. Therefore, 8u equal to n pi, and therefore u equal to n pi by 8. These are the fixed points. Then all periodic points, f of u is given by minus u cube, right? So we have to take fk of u, we have to make fk of u equal to u. Then u is a fixed point of f with period k. If I find f square, f of u, that is f of minus u cube, you will get u to the power 9. F cube of u, f of f square u, f of u to the power 9. Again we get minus u to the power 27. So fk of u equal to u. It is there only when u equal to 0. Otherwise, the power is increasing here. And therefore, 0 is the only point which is periodic, isn't it? Periodic point with period 1. That is it is a fixed point. U equal to plus or minus I is also periodic point with period 1. Okay, U equal to plus or minus I is also periodic point with period 1. So this is about fixed point, periodic point, and stable subspace. So for today, we will stop here, and the remaining will go in second.